see the determination of enthalpy of a combustion using bomb calorimeter. So this is called a bomb calorimeter. The inner vessel is called bomb. So this is the bomb. Actually, it is made up of strong steel coated with a silver or platinum or any other non-oxidizable material. Steel. So here is a stirrer to stir the water. The substance what you are actually taking is getting burnt inside this bomb, and the heat is dissipated to this water, and the stirrer, it homogenizes the water in temperature, and here is a long thermometer to measure the temperature accurately. Actually, the outer layer is a double-walled layer to avoid the heat loss by conduction and convection and even radiation evacuated. Now, what we are doing now, this is actually the bomb. So here is an oxygen supply and a screw to adjust the supply of oxygen. And here is a small tray, that is a platinum cup, in which the substance that is to be burnt will be kept. And here is a tungsten wire, and this tungsten wire is electrically heated to ignite the substance taken in the platinum cup. And the entire setup is made up of a very strong steel, and the inner part of this steel is coated with gold or platinum or non-oxidizable material. Normally what happens when the substance is burnt in the bomb, the outer part of the bomb is getting heated and the heat is transmitted to the water, and the stirrer is stirring to keep the temperature of the water uniform throughout, and the temperature rise is noted down using a thermometer. So what is actually to be found out is the Z, which is the heat capacity of the thermometer, capacity of the calorimeter. Now the theta is the rise in temperature, mm is the molecular weight, m is the mass of the substance taken. Normally the Z is water equivalent is unknown. In order to find out the Z, a reference material is chosen, and the reference material is a one whose molecular weight and its enthalpy of a combustion are accurately known. So if you take the benzoic acid, you know its molecular weight is 122, and also its enthalpy of a combustion is minus 3226.7 kilojoule per mole. So knowing this particular value, your known mass of the substance is taken and it is completely burnt with the help of the bomb calorimeter, and the QV is known and Z is not known. Theta is the rise in temperature, mm is the molecular weight of benzoic acid, and m is the mass of the benzoic acid taken. With this you can calculate Z. Normally QP, that is the heat energy supplied or transferred at a constant pressure condition, is equal to the heat energy supplied or obtained at a constant volume condition plus delta nRT. This is how the QP and QV are related. So with this equation, you can find out the QP. So even to find out the QP, you have to know the Z, which is the water equivalent of the bomb calorimeter, which is found out using the reference substance, QV, and the molecular weight are known. So this is the construction and the working of the bomb calorimeter. Now you see, when you do this problem, you can understand. Look at here. Normally I take 0.5 gram of benzoic acid, and the temperature rise is found to be 0.55 degrees centigrade, and the thermal capacity of the calorimeter, that is the EZ, is found to be 23.85 kilojoule per Kelvin. So now I'm going to calculate the enthalpy of a combustion at a constant volume condition. So according to the equation, Z into theta into molecular mass divided by mass of the substance taken. So which is equal to 23.5 kilojoule per Kelvin into 0.55 Kelvin. See, degree centigrade and a Kelvin here, they are taken as the same because it is only the rise. It is not the actual temperature. Suppose previously the temperature of the water is 22 degree. Now it is 22.55 degrees centigrade. So the difference is a 0.55 degree centigrade. So as the calibration is the same for centigrade scale and the Kelvin scale, the 0.55 degree centigrade difference can be taken as 0.55 Kelvin difference. But if you are measuring the actual temperature, then you have to correct it by adding 273.15 to get the absolute temperature scale. But when you think of the difference in the temperature, just you keep the difference as such. So the rise in the temperature is 0.55 degrees centigrade, so which can be kept as 0.55 Kelvin, and also the molecular weight is 122 gram per mole, and the weight of benzoic acid taken is 0.5 gram. So from this, you can calculate the QV is equal to minus 3200.7 kilojoule per mole. Now what happens when you look at the actual combustion reaction? When you look at the actual combustion reaction, benzoic acid reacts with 7.5 molecules of oxygen. It gives 7 molecules of carbon dioxide and 3 molecules of water. So the delta N is the number of moles difference between the reactant gaseous molecules and the product gaseous molecules. So on the product side, we have only 7 carbon dioxide molecules. Minus on the reactant side, we have 7.5 oxygen molecule. So in the entire reaction, only the oxygen and the carbon dioxide are in gaseous state. So 7 minus 7.5, you are getting minus 0.05. So at a constant pressure, the QP is going to be minus 3200.7 plus delta N, which is minus 0.5 into RT, where R is the universal gas constant 8.314 joule per Kelvin per mole, and into temperature is the normal temperature and pressure 298. So what you are getting is minus 3201.9 kilojoule per mole. So this is how the bomb calorimeter is used to measure the enthalpy of combustion of various materials. Now, next, another important topic is bond energy. Bond energy for any particular type of bond in a compound may be defined as the average amount of energy required to dissociate, that is to break, 1 mole, that is Avogadro number of bonds of that type present in the compound. See, it is also called enthalpy of formation of the compound. So the energy spent to break the compound is the same as the energy released during the formation of the compound. So enthalpy of formation and the enthalpy of bond breaking, or in general I can say the enthalpy of a bond making or enthalpy of a formation or bond energy, all are one and the same. Maybe then and there the signs will change, but all other things are one and the same. Now enthalpy of formation of compound is an additive property. You have to add. Say I have put down a few bond energy values. See, in order to break a hydrogen molecule into 2 hydrogen atoms, the energy supposed to be spent is 435.1 kilojoule. For an oxygen to be broken into oxygen atoms, it is 489.5 kilojoule. For nitrogen to break it into 2 nitrogen atoms, it is 937.4 kilojoule. For solid carbon to gaseous carbon, it is 719.6 kilojoule. So the enthalpy of formation of methane, now you can calculate. I go to the next slide where it is clearly written. See, I want to calculate the bond strength of CH in methane. So when you just, for the formation of methane, you have to take solid carbon and to convert it into gaseous carbon, for which you have spent delta H 719.6 kilojoule per mole. For hydrogen, there are 4 hydrogen atoms are needed. So 2 hydrogen molecules are to be broken. So it is 2 times 435.1, because this 435.1 is presented in the previous slide as it is used for the breaking of 1 molecule of hydrogen to form 2 atoms. It is 435.1. Now, for the formation of methane, 4 hydrogens are needed. So 2 molecules are broken. So delta H is equal to 2 into 435.1. It is 870.2. So the total amount is 1589.8 kilojoule. But what happens now? You already know the enthalpy of formation from various other data, which says that the enthalpy of formation of methane is minus 74.9 kilojoule. Now you subtract the total energy spent to accumulate various atoms for the formation of this compound, which is 1589.5. You subtract this from the enthalpy of formation. That is what is done in this step. What you are getting is minus 1664.7 kilojoule. So this minus 1664.7 kilojoule is for all the 4 CH bonds. But according to the definition, let us read the definition again. Bond energy for a particular type of bond in a compound may be defined as the average amount of energy required to dissociate, that is to break 1 mole, that is Avogadro number of bonds of that type present in the compound. So what happens? By this calculation, the value that you have attained, minus 1664.7 kilojoule, is for 4 CH bonds. So for 1 CH bond, it has to be divided by 4, and what you are getting is 416.2 kilojoule per mole. Suppose if you take the same thing for ethane, in the case of ethane, there are 2 carbon atoms and 6 hydrogens. So it is 2 into 719.6. So what you are getting is 1439.2 kilojoule. And also for hydrogen, it is 3 molecules of hydrogens are to be broken to get 6 hydrogen atoms. So it is 3 into 435.1. You are getting 1305.3 kilojoules. So total it is 2744.5. So now the enthalpy of formation of ethane is minus 89.2 kilojoules. So from this value, you are going to subtract 2744.5. When you subtract it, and finally you got the bond energy as minus 2833.7 kilojoule. But this particular energy is for all the bonds present in the ethane molecule, which is C and then 6 CH. So totally, let me put this CC bond as X and 6 CH bond. This value I am taking from the methane. So it is 416.2. So from this, that is 6 into 416.2 plus X will be equal to minus 2883.7. So from this, X is found to be 347.3 0.3 kilojoule. This is how bond energies are calculated. And using this method, the bond energies of various bonds like C double bond O, C triple bond C, C N, NO2, all these bonds are calculated using this calculation. Now, what are the applications of bond energy calculations? This is another important thing. The first application is determination of enthalpies of reaction. Certain reaction enthalpies cannot be directly found out experimentally, for which we have some indirect methods. Now we have a calculation method to find out the enthalpy of reactions. So for example, ethylene reacting with hydrogen to form ethane. What is the enthalpy change accompanying this particular process? The enthalpy change accompanying this particular process is there are two bonds broken. One is the C double bond C bond broken, and the hydrogen molecule is broken to hydrogen atoms. And the new bonds formed are one CC bond and two CH bonds. Because the four CH bonds are remaining unaffected. So whenever there is a bond breakage, it has to be written as the energy that we supply in positive sign. What are all the new bonds formed? The same bond energy has to be given in the minus sign because the heat is evolved when the bond is formed. So look here, it is minus delta HCC plus 2 into delta HCH. So bond broken delta HCC plus delta HHH. So if you substitute the values of these bonds, bond energies in these places, you are getting it is minus 347.3 plus 832.4 plus 615.0 plus 435.1. So when you simplify this, you are getting it is minus 129.6 kilojoule. But the experimental value is 133 kilojoule, which is very close to the experimental theoretical value. So we can say that the theoretical value that we have calculated is correct. So the next one, determination of enthalpy of formation of compounds. And you can see here, I'm taking 3 carbon gaseous atoms, 6 hydrogen gaseous atoms, and 1.5 molecule of oxygen, and you are getting this acetone. Now, if you want to find out the enthalpy of formation of acetone, you have to find out the various bonds broken and the various bonds formed. The bonds broken are 3 carbon solid molecules are to be converted into 3 carbon gaseous molecules. And also 3 hydrogen molecules are broken down into 6 hydrogen atoms. And also half a molecule of oxygen is broken down into 1 atom of oxygen. So what are all the various bonds formed? There are 2 CC bonds, 6 CH bonds, and 1 C double bond O bond. So here also for the bond breaking, you put it in the positive sign, and for the bond formation, you put it in the negative sign because during the formation of the bond, energy is given out. So the delta H formation becomes 3 into delta HH and half into delta OO and 3 into delta CSCG. That means the total amount of a carbon should also be supplied by converting the solid carbon into gaseous carbon. So that is why 3 into delta HCS to CG and minus 2 delta HCC, that is 2 carbon-carbon bonds are formed, and 6 carbon hydrogen bonds are formed. So 6 into delta HCH and delta H into C double bond O. So all these values are available in the literature. When you substitute these values in the appropriate place, you are getting minus 184.25 kilojoule per mole. So this is the enthalpy of formation of acetone. Enthalpy of formation of acetone. Now you see. This is the last application. This is determination of resonance energy. Normally, we can calculate the enthalpy of a formation as we have done in the previous example. And the enthalpy of formation can also be experimentally found out by complete decomposition and other things which we have already seen. What will happen if benzene is dissociated? You will be getting 6 carbon gaseous atoms and 6 hydrogen gaseous atoms. So the dissociation involves the breaking of 3 carbon-carbon single bonds, 3 carbon-carbon double bonds, and 6 carbon-hydrogen bonds. When you substitute these values, you are getting 5384.1 kilojoule per mole. That much of energy has to be used to break the benzene into individual atoms. But when you calculate the same value, when you find out the same value experimentally, you are getting 5535.1. So as per the formula, as per our calculation, the value is a little bit less. That is 151 kilojoule per mole less than. Calculate the value. So this value minus 151 kilojoule per mole is the extra stability of the benzene due to resonance. So that is why we are assuming the resonance structure like this. It is double bond sometimes here, here and here, sometimes it is in the other carbons. So this resonance is increasing the stability of the benzene, which is called the resonance energy. So with this, we are completing